Hey boys and girls, welcome back to Munro Live. I'm here at Saku with Arvid Nevestroy.
Yes,
it came close. And we're going to be looking today at something that I am extremely interested in. Saku is the only company that I know of that has a chance at really being called a solid state battery. And the reason for that is because all their stuff is dry. And so we're going to have a look today at pretty much everything that they're doing, except for the secret sauce, correct?
That is correct.
Yes.
Sandy,
so,
welcome.
Oh, thank you so much. Thank you. So you're explaining a little bit to me. Saku is not a Japanese surname, right? So what is the meaning behind Saku?
It interestingly also has a Japanese background, but
Oh,
firstly,
really?
in Persian language, it's called platform. It's the word for platform, and that's exactly what we are developing: an additive manufacturing, 3D printing platform that can combine several materials, several processes, and hence makes better batteries. In Japanese, the Saku stands for something to bloom, to come out.
Right. Yeah.
Which is a nice coincidence with the Farsi language, where it means platform.
Okay. So I guess the best thing we can do is you have a little 3D model over there, and I was wondering if maybe we could talk about the chemicals that you're using, or the additives, or the basic metals that you're using, and then maybe have a look at that little 3D model so we can, get a grasp of how it works and whatnot. So the only thing I'm going to ask is, because we have a very mixed audience. Mm-hmm. We have people that are, no question about it, PhD engineers and what, but we also have people that don't know as much. So if you could know acronyms and and keep it on a level that that everybody might be able to understand.
Okay, I will do.
Great. Okay, good. Let's go
over.
And have a peek. Yeah.
So before we turn really to the additive manufacturing platform, where we have this model here, I want to explain a little bit where we come from, what we make differently, right? So today's batteries, as most people know, right, they consist of various layers of material, active material. There's typically a current collector made out of copper on one side, the anode side. There's a cathode side with aluminum foil, and then you add the layers to this. For example, we are working with lithium metal in the anode, which is very, very rare. And you see here, this is lithium metal on a foil. It does react with air, so the sample always becomes bad after some time. Yeah. But this is what a conventional battery looks like. Now, if you put these layers together, it at the end, in the conventional way, right? The conventional manufacturing that everybody does today looks like this then, where you just stack cathode layers together, you stack anode layers together, you wrap a separator around it and between it, and then this becomes your battery. And you see here that's with lithium metal on the anode too. Now, if you put this together, then at the end today, you put it in a pouch cell so that it's sealed from the outside. And this is then typical pouch cell, right? Small format. That's what everybody does today. Mm-hmm. What Saku has developed is firstly a new electrochemistry that we put in this pouch cell format. An electrochemistry that has lithium metal in the anode. And that's a very, very superior technology, because the energy density is much, much higher if you do that. So the densest form to store lithium in a battery is as a metal, lithium metal, and not in graphite or in silicon graphite or other materials. Yeah. And this is what we do here. So we use lithium metal in the anode, and that allows us to reach much, much higher energy densities. While today the market is typically around 600, maybe 700 watt-hours per liter in the cell, or maybe 730, we are already exceeding the 800 watt-hours per liter in a cell, on a cell level. Right? So this chemistry that we have developed at Saku exceeds the performance criteria that are out there in the marketplace.
So not only is it volumetric, but you also have a gravimetric advantage as well, right? It becomes lighter.
That's right. Lithium metal is also lighter, right? And because the layer is much thinner, there's less weight also. And this is another direction we're working on, also to improve on the watt-hours per kilogram, but also watt-hours per liter, right? Both are important, and some are more important. For example, any vehicle that drives typically per volume is more important, because there's not much space to put the battery in. Everything that flies, that takes off, typically the weight is more important, right? Because you cannot add more weight, but not add the power to actually make it lift off. So that's an important criteria there.
So there's one other thing too that it just dawned on me. You mentioned that people are putting the different metals together and whatnot, but the one ingredient that makes yours different than everybody else would be the electrolytes. And the electrolytes in a standard battery come in usually just before you stick it in a pouch or just after you stick it in a pouch. So that saves me from answering a whole bunch of questions from people. Well, wait a minute, where's the... So that's kind of how it works. It's going to be put together, then it's going to go into maybe a pouch or whatever, and then electrolyte goes in and that's what makes it active. So, but yours does not, correct?
Yeah, so in this battery, we still have liquid electrolyte in it.
Yeah.
That's still the conventional way. And we developed this in-house because to work with lithium metal, it's very different from other typical materials inside. So we developed this electrolyte ourselves. But as we move to the next battery generations and also to our printing capability, that's where we make the materials, more and more of them, completely dry and solid, right? Mm-hmm. But we don't have a full solid-state battery today yet, but we're working on this, right? And we see that the manufacturing capabilities and the way how you manufacture it are really a key enabler to get to solid batteries at the end, because the process is different, how we put materials together is different, and that's why we believe the manufacturing technology will be one of the enabling factors to get to all solid-state batteries.
And that's a great segue to this,
yeah,
correct?
Yeah, maybe just one more second on this side here. So as we move to additive manufacturing, key advantages, of course, additive manufacturing, or call it 3D printing if you want. You can firstly design the shape and form that you want, right? For example, this is a shape and form that we have designed for a battery, and we'll show you later. I can show you later a complete battery out of this. So you can design the shape and form, which is very interesting, of course, for special products that don't have necessarily a rectangular space inside, or cubical or cylindrical, which is not very good packaging. But you can decide the shape and form. And at the same time, though, we made it fast. So it's not slow 3D printing like everybody knows, right? It's industrial speed additive manufacturing. Another advantage is you only add material where you need it. So it's not like you coat a lot of material and then you cut it away and have scrap, but you only add it where you need it. Now, in order to add it and do it in additive manufacturing process, you need the right material properties, right? And here we have some examples of materials that behave a different way. And this would same way apply for cathode and anode material. You see, if we use this powder, which would be a battery material, it doesn't really move very well. If you want to lay it down, imagine you lay this down on a surface, it's not going to be very uniform. But what we do at Sakuu is we change the material. You see here, looks like a liquid, but it actually is still a dry powder, right? So
a dust.
We have the know-how in material science to adapt the materials to the process. So if you don't do this, you cannot 3D print battery materials. Right? You have to do that. You have to change the material properties, right? And we do the same for cathode material. This is conventional cathode material, and we'll see in the lab how this looks like after we have treated it and made it capable of being 3D printed. Yeah? So that's the enabling technology that we have at Sakuu. We have developed a battery to show everybody we can do batteries. We can even do a very innovative battery. Yep. And we can even use the lithium metal, and we can even use it in printing, in the additive manufacturing. And now we have the materials ready, and now we put it on an additive manufacturing platform. Right? And that platform, this is a 3D print of the additive manufacturing platform. We call it caveon as a product name. And this is our first unit that we have built, which we use to develop all the process capabilities. So we have a dry process on the front side where we deposit dry powder, like this powder that I just showed you, the cathode powder, in a way that it makes a good battery layer. So it must be very uniform, it must be very dense, it must at the end be well conductive for ions, for electrons. So all of these electrochemical properties that the battery needs are enabled by doing this process. So we're depositing it, and how we deposit it is very much our trade secret, because that's the secret sauce here we talked about. And then it's calendared, which means pressed together. And then with quality control along all the steps, we create a layer of battery material, like a cathode layer or an anode layer, right? Mm-hmm. This additive manufacturing capability we have here also includes the possibility to work with several different materials. So on the second side of the platform, we are capable of applying various materials with a different 3D printing process. For example, an inkjet process or a material jetting process. So the capability we have developed with this machine is to use multiple materials with multiple different processes and put them all in one device. So if you compare to today's additive manufacturing, 3D printing, companies either build a metal object or they build a polymer plastic object or ceramic object, but it's always one material. But we can print several materials using different processes in one device at the end. And that's just one of the devices the one we're focused on right now is a battery, right? Because if you can print battery, you can print many other things. And at the same time, it's very fast. So it's not the idea of conventional 3D printing where a nozzle moves around an object and it takes forever to deposit the material. But the process is made in a way that each station of this platform runs continuously, and this way we achieve the speed of the overall output.
So what is the station timing, or how many jobs per hour do you get out of this machine?
So with this one, if we would just do battery, we would be able to produce 2.5 megawatt hours per year battery capacity. But we're now working on the first industrial scale one, which will be around 100 megawatt hours per year.
Okay, so that tells me per year. I'm just looking at station spacing or station timing as they moves through. So for instance, it takes about 60 seconds to get a car off the end of the station or off the assembly line, unless you're Tesla, and then it's 43 seconds. So what would be the station spacing here? What would be the timing to get something through the whole system at a production rate?
See, typically it would be seconds, a few seconds per battery. Now it depends, of course, very much on how big the battery is. The big difference with this technology is you don't have the possibility to just make one battery format, but because it is 3D printing, you can decide with your computer how your battery shape will look like. Right? So let me quickly show you one example here. So the battery cells that come from this machine would be cells like this, which are one cell. This is the anode side, this is the cathode side, the conductive surfaces of the active battery sealed around it. But you could make this in any shape and form, right? You can make a different shape. You could even put holes inside if you want to do cooling thermal management lines in it, right?
A lot of
or
things,
align it to the product that you have. So you don't design the product around the battery, but you design the battery into the product. So that's why how many cells per minute is hard to say right now, because it depends on what you do. Right? So that's why we measure it.
But if it's a few seconds, can I say something like 15 seconds, 10 seconds?
10 seconds would be...
Okay, so that would mean that you could crank out easily enough batteries out of one of these machines. If you were looking at a line of them, I'm certain that I already saw some of the drawings and whatnot. You have several of these things in a row, so you get parallel processing. So getting a battery at line speed right now is pretty difficult for almost everybody. But with yours, it sounds like you could maybe be able to generate enough battery pack to supply to the vehicle, which was going down the assembly line at 60 jobs an hour or one a minute.
Yeah, absolutely. So imagine, let's say, when you talk about EV battery factories, you talk about the gigawatt hour factories. Right? So for 1 gigawatt hour factory, you would need 10 of these machines roughly, or 11, right? If you have a little bit of maintenance downtime. So 100 megawatt hours, 10 times is 1 gigawatt hour per year. So you would have maybe 10 to 11 machines of this to have a 1 gigawatt hour manufacturing capacity. And then depending on how big the battery in the EV is, right? If it's 100 kilowatt hours, that's a certain number of cars that you could provide batteries to.
And most people, at your volumetric and gravimetric status, the thing you've got right now, that would mean that I could probably get maybe over 100 kilowatt hours, because it's going to be slightly smaller and it's going to be lighter as well. So that's going to give me range as well. So weight, we've talked about, what really and truly is important for range. It isn't just necessarily a big battery, because, as you know, some of the cars with the biggest batteries go the shortest amount of distance. So if we're looking at, did you say 10 of these? 10
of these would be
okay, so
1 kilowatt hour factory.
What sort of footprint would that be? How many square meters? Or
Yeah, the footprint is much reduced. So this is now 60 feet by 6 feet, right? So it's
so
very, very small.
2 by 10 meters.
And you will see later when we look at the pilot line, you see the pilot line footprint that we have right now is more than 10 times bigger, right? To make a complete, in the conventional way, right? How we build these battery cells that I showed you before, the current lithium metal cells, is more than 10 times more footprint, right? So we put all the process in one machine here. And see, the founding team of the company Sakuu has come from the semiconductor industry and did additive manufacturing also in the semiconductor industry. And the industry is well versed in making very complex material science processes in one big automated machine.
Correct.
So that is the know-how that we are building on, and the experience that the team has, also our manufacturing team from the semiconductor space, to really manage these processes at high precision and very effective setup, very efficient setup, small footprint, and of course much less costly, right? So this line, this platform will be much less capital expenditure than a normal setup to do conventional wet coating. We talked about the solvent recovery, the scrap material, because you don't have additive manufacturing, and the solvent you use, the toxicity, the energy you use, so all the evaporation and the heating. So all of this will be much less capex, much less opex, and at the same time be able to design the battery into the product and not the opposite way.
Well, one thing that I would like to touch on is scrap. Can we just come over here for a second? So let's just look at this part right here, and I'll try not to bend anything. But you can see that usually you start out with something that's a full size like this, and then what winds up happening is I only want that part. This becomes scrap. Now, imagine what would happen if all I wanted to do was make that, and I used additive manufacturing. How much scrap do I have? Like nothing. So this is kind of one of the things that we're looking at is scrap. Sometimes this can be recycled quickly, other times not. But looking at scrap and waste is extremely important in every process. So I'm going to be giving a speech on gigacastings. And the gigacasting itself doesn't really save you a ton of money. It doesn't really save you a ton of weight, although it's around between 8 and 10%. And a lot of other things. But when you start looking at waste and scrap, okay, if you have scrap, and most people are getting about 3%, I just remelt it. So it's not like it goes into a dump somewhere. It just gets chewed up and remelted, and it goes back in. With additive manufacturing, there is some powder that it doesn't get used. But at the end of the day, the amount of waste or scrap is minimal, because I can take the dust and I can use it again.
Exactly.
So this is why I'm so excited about additive manufacturing in battery manufacturing, because if you look in the backs of most battery companies, sooner or later you're going to find great big giant tubs of copper, of sometimes lithium, all kinds of different materials, and they basically go to recycling, or they'll go back to a manufacturer to be chewed up, cleaned, and reused. But sometimes, like in the case of this, once it starts corroding, now you've got something that's going to take you a bit to get the ingredients taken apart again, and in some cases you can't. So I don't want waste, I don't want scrap, and additive manufacturing gives me what I really and truly want, which is a product and no scrap and no waste.
Yeah, and there's two aspects to it. So one is we use less material in the first place. So
Yeah.
this is not creating scrap. And if you use it this way in a dry process without any solvents, if you do your process, this powder still remains this powder, right? So you don't
Yeah.
even need a recycling process
Exactly.
before you can
Yeah,
reuse it.
right.
So that's the second aspect, right?
Yeah, and it's,
So it's
yeah.
a lot of advantages come when you
Yeah.
go to doing this additive manufacturing process.
To me, that's why I wanted to come here. This is a really exciting new way of making products. And people have always said, oh yeah, well, additive manufacturing is okay if you want to make toys or a model of something that we're going to do in, in rugged manly steel or something. But now what I'm looking at is something where we're going to see stuff at production rates that we'll see a huge footprint reduction. And then, as you mentioned, solvents and electrolytes and whatnot, they have to be recaptured. So Tesla, on their dry product, went from something where, let's just say the line was about that long, and now it's about this long. Yep. And all of that has to do with how they do calendaring, compression of the different materials and whatnot, how they make them adhere, and that's kind of like their magic sauce. So hopefully we'll see how you do it.
So this is I think you've seen this before. This is the outcoming cathode roll, right? This is a carbon layered aluminum foil, so we're not yet coating at this point in time, but we're getting the machine ready. So this is how you typically, obviously, make cathode layers, anode layers, and this is the big process that consumes so much energy, has the solvent recovery.
Right.
This is what we will get rid of, right? And as we discussed, these lines are much longer when the speed of the process is much higher in a big manufacturing site, and consumes a lot of energy, right? The solvent goes up, it has to be recovered. It's toxic material that is a hazard always in managing for employees. So this is something we want to get rid of.
So let me ask you a question. Did you buy this equipment, or did you have it manufactured to your spec, or did you build it yourself?
We bought this equipment sort of off the shelf, right? We needed it to develop our battery technology and our battery expertise. And as we develop this lithium-metal battery, we are now taking this chemistry, these components we have developed that work together as a battery, and we now put them on the additive manufacturing platform and use the same materials to make batteries that are printed.
Well, one of the reasons I'm asking is because we used to have quite a number of machine tool companies that would make this stuff, but this kind of looks like Chinese equipment that we saw lots of when I was working with the Chinese battery companies. Is this from the States, or is this from Europe, or is this from China? Or?
This is at the moment from China, and see, that's one of the activities we are also focusing on. We want to be US based, right, in our material sourcing, in our equipment making, and the equipment we're developing, we don't depend on other countries at all.
Yeah.
Right? We do it in the US, and that's very important for us. And another aspect we haven't yet touched on is when you do additive manufacturing like we do, you start with the raw material, which is the powder,
Right.
and you print the whole battery in your platform. So there is no complex supply chain like today, where you maybe buy cathode here, then ship it to Asian countries to coat it, and then you ship it back. So all the logistics, all the supplier management, that goes away. You just need raw material.
Right.
And the raw material, most of the raw materials you buy from global chemical companies off the shelf today. So there's no dependency that has any geopolitical challenges, right?
Yeah.
And that's one big aspect of bringing this technology back into the US.
It's funny, these machines used to be made in the US. They went to China. The Chinese figured out how to make them. Now they're selling them back here, and there's virtually no US companies that make these things now.
Yeah.
They're not unknown, but they're very hard to find. So having this disappear in the form of 3D printing, which those machines are manufactured here, is a good thing, I think, for the US.
Yeah, it's a good thing. So for all of the Western world, right? It's independent. For every country who does it, who wants our additive manufacturing platform, it increases the independence of any geopolitical
Yeah.
interferences, right?
Works for me.
That's good. Yeah. So see, there's not only energy consumption, there's a lot of noise to it too, right?
Yeah.
And this is what we really want to get rid of, right? We're using it right now to make all the samples. That enabled us to go to this very high energy densities, more than 800 watt-hours per liter already, because we established a very well-controlled and managed production process and quality. Okay. So typically, of course, we put cathode in these bins there, in these jars, and then it's supplied to the machine, and then coated on the layer that we move through the machine. Right? But this is the conventional process, right? Which we won't have when we do additive manufacturing.
Actually, we've shown a couple of these things in the past, and people have asked questions like the main one is, how do you make sure that the film stays in the center? And I've talked about crowning, and I noticed you were just adjusting it. So at the end of the day, it's kind of when you're in a machine like this, kind of a manual process. You have to have somebody who really knows what they're doing. Otherwise, this thing starts to drift.
Yeah, it's a lot of experience,
really,
a lot of fine-tuning, right, to get it right.
Yeah.
And but once it's running, it's very stable. But of course, you want to run in the continuous
well, first you
way.
got to tune it.
Yeah,
and, then,
and the tuning is hard here because it's then the liquid slurry, right? It has certain viscosity, it does certain things, certain behavior, and this is the know-how that we then transition to the additive manufacturing process, where similar requirements are there, but the way to manage them are different, right? Because of the powder situation.
Yeah, absolutely.
So these are now the components we put in our lithium metal battery, right? That we have made in-house here. This is the cathode, and then this is the lithium metal anode, right? And these layers are then assembled in our battery. We call this battery, by the way, Cypress battery. That's the product name of the battery. This is what we are licensing. So we're licensing to any interested parties the product, the electrochemistry, the process, the supplier selection, the equipment selection, everything, so that any manufacturer, as we just discussed, who wants to be in the US and manufacture batteries, can just take anything from us and get started. Right? The technology is fully developed. And these are the components that go then into the battery.
I'm not trying to get a date or anything, but I'm going to get nice and close to you. Okay, go ahead.
Yeah, go ahead. You can
So
say
this is a restacking machine. We basically layer the cathode and anode on this machine, and then with a separator, and then we take it to the next stages for battery assembly. So here we have the folding machine. We have the two cartridges for anode and cathode on the back side of the machine on here. And then this is the centering stage where the machine aligns the electrode, and then we have like two pick and place arms which places it on the stacking head, which layers it with the separator as it stacks up the electrodes, and then finally we get the stacked electrode in the end.
And these are the layers you're stacking one on top of the other, right?
So these are the anode and cathode that we're gonna.
Yeah, so this is pure lithium metal here, right?
Yeah.
This one. Okay, let's move it.
I'm gonna load the cartridges, and then we can get.
Okay, great.
Okay.
So first,
on the interface, we load up the number of electrodes that we are going to stack up, and then the tolerances according to the electrode thicknesses that we are stacking, and then we get started.
I see.
Now, the settings are loaded up. We're gonna start the machine.
Okay.
When we start the machine, the rear side pick and place arms are going to pick up the first set and have them centered. We have the cathode centered there and the anode centered over there. Now we are good to go. Now on, it's going to be a sequence of stacking. There wouldn't be any pause. We first place the anode. And then the cathode. So right now we are building a 9-layer battery. So it's gonna repeat this for 9 times,
Yeah.
and then we'll get the finished stack in the end. That's the last layer. It's gonna do one more job, so it can have an extra layer of separator on both sides. And then now we send it for the cell pickup.
Yeah. You want to come over here, Eric? Oh, do it.
Oh, it's done. Now we're gonna open that door and then remove the stacked electrode.
Okay.
Now we open this door. So this here is the stacked electrode, the core of the assembly. This is now going to be like taken to the next stages where we weld the current collectors with a tap and then take the welded stack to a sealing machine on here and then place it in the aluminum pouch bags and then seal it on 3 sides and then it goes to the next stages.
Yeah.
Now,
sounds great.
transitioning, thank you, Avi. Now transitioning from this to the additive manufacturing and printed batteries, we have some samples here we want to show to you. So,
Wow.
my name on it. So, this is now how we made a complete cell, like I showed you before, in a certain pattern, right? So, here's how we printed the the anode, the lithium metal.
Yeah.
This is the cathode, right? And these then fit together to become a battery, like I showed to you before, that has now this unique shape and pattern. And
So are we looking
So
at,
this-
does
so
this
this-
turn into the tab then? Is that why there's this angle then? This one doesn't have the angle. Does
Yes,
this turn
yes.
into the tab?
no. This is just the angle. That's the angle that the foil was this way, right? So,
I see. So,
but
and
the
then you
key
cut
thing
it.
is this is
Okay.
lithium metal. Right?
Yeah,
So we
yeah.
have printed lithium metal.
Correct.
Today, typically, you have to buy lithium foil with,
Right. Yeah.
like we saw just in the process, where metal is on the foil of copper. But here, with our process, we can actually apply lithium metal in the shape and form we want. Right? This
So-
is the advantage of additive manufacturing. And we can do the same for the cathode because we have the dry
Right.
powder process here. And then we can add a separator, or we can even additively manufacture a separator, which we can show you a sample later. And this then becomes this kind of battery, right? This is the
Correct.
cathode and this
Yeah.
is the anode.
Yeah.
So this is one of the enabling activities. We can print cathode in the shape and form we want, and see. And we would never fill this edge, right, and cut it away, because the expensive material is the cathode material, the black material,
Yeah.
or the lithium metal here, the gray material. And because we never printed where the holes are or printed where the corner
There's
is,
no
we
scrap.
have less scrap, right?
Yeah.
And even if we print this dry powder, we can reuse it immediately.
Yeah. Yeah.
Okay. So you can see here, this is on a carbon-coated aluminum foil, right? And you see here the black pattern. You see there's a rectangle here, there's a square here, rectangle here, a circle there.
Yeah.
I think hexagon is the right word.
Yeah.
So this is now coated cathode. Now it looks pretty trivial, but the big achievement here is that these layers of cathode material are capable to work as a battery, right? They have the right thickness, they have the right conformity, they have all the recipe inside to be a cathode, a working cathode.
Yeah.
And they're only applied where we need them, right? So this is exactly the advantage here of additive manufacturing, 3D printing. You only put material, you add material where you want it, and you don't make a full sheet and then cut it away.
So right now, how stable is that? I saw him pick it up with tweezers and whatnot. Nobody's been touching it with their hands. So is this still...
This is stable enough to move through a faster process.
but not stable enough to pick up with your hands?
We wouldn't do it right now because then
It'd be ruined.
One of the powders could move, but this would go then in the next process. The cathode is one of the next processes, right? What you always do with a cathode.
Yeah. Right.
So it's going to be absolutely stable to go through this next process and then be fully functional as a cathode.
Yeah.
Right.
Yeah. So again, calendaring means that I'm going to basically just press it. It's going to be pressed together.
Yeah. So, but it has the full recipe already in it, right? So it really is, and this takes some engineering work and know-how how to make this powder now be very conform, very uniform layer, but still work as a battery with high performance as we want it, right? So the high performance that we have in our battery that we have developed, we are now transitioning into additive manufacturing. Right?
Great.
And that already works. So we have some example cells here which are actually printed, fully printed.
Yeah, this one is the actual one.
Yeah, so this one is an actual one. This is, can you touch it here? Okay. So this is anode side, right, and cathode side with aluminum, and it's an active cell, right? That's exactly how a printed cell will look like. So you want to take this multimeter here, 1.8 volts.
1.8 volts, yeah. So this is, you're getting this?
So this is one of the world's first printed battery cells that have actual voltage, right?
Perfect.
So we had some older samples here too, but this is how this works at the end, right? You put all the active materials inside, you just seal it, there's no pouch, you just have the cathode, the current collectors, and this is your printed cell.
So what would happen after this is you're going to bake, I don't know what your pack's going to be, but let's say that it's 10 volts. So this is 1.8. I would just add more cells, one on top of each other.
Yeah.
It'd be in series. I don't have to do anything else.
Yeah, that's not fully charged maybe right now, so it could be like in lithium metal, it would be probably around 3.7 volts, right? Then you can, let's say for a power tool pack which has 20 volts, you would just add 10 together, right?
10 or 11,
together.
Something like that. Yeah.
What you want.
So, and this is going to give me a very, very thin package. So if you look at that, we're looking at a couple of thou. Anyways, so now I start packing it up, and then it'll go into something, I assume, maybe some sort of a plastic package or something.
No, you don't need anything. You would just pack it in the battery pack.
Yeah, well, that's what I'm saying. The battery pack,
whatever battery pack,
whatever you make it out of plastic, probably, and then that would add that, and so you'd probably wind up with something that's going to be a couple of centimeters thick at the most.
Yeah, depending on how much
millimeters, a few millimeters.
Yeah, this is less than a millimeter. This is just maybe.
No, I mean if I was making a whole pack, I might wind up with maybe 12 or 14 millimeters, something like that, and I've got a 20 volt pack.
Yeah, 20 volt pack, roughly. Yeah.
So that much. Yeah. So this is why I'm really excited about this process.
And this is now still
so many.
Sorry.
Go ahead.
And this is now still rectangular, right? Now
the
machine could do it any shape, right? Like we just saw the results.
Exactly.
So you can then really design it into your space that you have in your product.
Correct.
Yeah. And not only in 2-dimensional, but also you could stack it in 3 dimensions, right? You make every layer a little bit different.
Yeah, right.
Adapt the energy in the battery because the computer controls what you do in every step.
Correct.
And that's how you build an additive manufactured battery that is optimum for the package that you have in your product.
Exactly. Okay, boys and girls. First, thank you so much, Arvid. This was really, really a good tour.
Thank you.
I am very impressed with the technology. I love the idea of additive manufacturing. I saw machine tools that, okay, we took one picture, but at the end of the day, I saw what I was really coming to see. You're a lot closer to what I would classify as manufacturing than pretty much anything I've seen so far. So this was a very, very good very good tour, I should say. And I'm looking forward to seeing the next steps. Like you mentioned a few things that unfortunately we can't mention right now, but at the end of the day, this is looking really, really like the future of additive manufacturing at production speed for automobiles. So I'm delighted.
Thank you very much for coming and for your interest, and we'll keep you up to date.
Well, thank you so much.
Progress.
Yeah. Okay. And thank you for watching. Bye now.